Now, in the previous chapter, we talked about how mass spectrometry can be used to determine aspects of a molecule structure. And, but I said that's just one piece of the spectroscopy that we're going to learn. So, this chapter, we're going to cover infrared spectroscopy, which is also abbreviated as IR, and ultraviolet visible spectroscopy, which is also abbreviated as UV VIS. Now, in mass spectrometry, you had a vaporized sample, it was ionized, and the mass to charge ratios and relative abundances of the resulting ions were measured. IR and UV vis works a little differently. It studies the interaction of electromagnetic radiation, which are photons, right, light, with matter. And so when we look at this, we're going to learn about the principles, and then we're going to learn how to apply it, and then we're going to look at some examples. So, again, both of these techniques are used really frequently. I used both techniques in graduate school, and they ended up in my thesis. So this is very, these are really, really common. So I want to start off with a review, and this is really a review of general chemistry material, and I want to review light. And so when we talk about light, we remember electromagnetic radiation, and it's abbreviated as EMR, right? And we did a whole chapter on how light has the characteristics of both waves and particles. Now, it behaves like a wave, so I want to review some things about waves. It exhibits an oscillating, which just means it goes up and down, electric and magnetic fields that can be assigned a wavelength, right? And that's just the Greek letter lambda, so you see that there. And it can also be assigned a frequency, right? So how many times the waves pass a certain point. So this has a higher frequency, right? Because more waves would pass a certain point than this one would. So what we see here is that if you have a longer wavelength, you have a lower frequency because not as many waves are going to pass. And if you have a shorter wavelength, you're going to have a higher frequency because more waves can pass. Okay. Now, frequency is also is the symbol for that is nu. It's the Greek letter nu. And these things can be related with the formula C equals lambda nu, which can also be arranged, right, rearranged in many different ways. I want you to remember that C is the speed of light. It generally is 3.0 times 10 to the 8th meters per second. I think your book uses 2.99. It's not a big deal. That is fine. And then I want you to remember that frequency and wavelength are inversely related. That means as one increases, the other must decrease, and that's what we see here. Now, as we're dusting off these brain cells, I want you to remember that each photon has a energy that's associated with it, right? And so we can, this light energy can behave as particles, as well as waves. So when we talk about it as a particle, we are talking about it as photons. Okay, so these little packages of light are these photons. And each photon is going to possess a characteristic energy that's going to depend on its frequency or its wavelength, depending on what information you're given. And so remember, we have the energy of a photon equals h nu, where the nu is the frequency of that photon. Now, h here, remember, is Planck's constant. Always misspell Planck's. It's CK there, constant. Now, these constants will be given to you. Planck's constant is 6.626 times 10 to the negative 34th joules times a second. Again, you don't have to memorize the constants. You don't have to memorize the speed of light. You don't have to memorize Planck's constant. I will give those to you. Now, we also know because frequency equals the speed of light over the wavelength of a photon, that the energy then can equal Planck's constant times the speed of light over the wavelength there. Now, the energy of a given photon is directly proportional to its frequency. So as frequency increases, so is the energy going to increase. Okay, and so that's one of the things that we see there. So still general chemistry here. You should remember the electromagnetic spectrum. When we look at this, when we look at electromagnetic spectrum, what we can see is really just a small portion of the electromagnetic spectrum. It's just the visible region here. So the spectrum's divided into regions. And so here's our visible light. Now we're going to look at the end of this chapter, how visible light interacts, or how we can measure the concentration of solutions of compounds that have visible light. And so we'll talk about that. So visible light is something that we're really interested in. We'll talk about that with UV VIS. We'll talk a little bit about ultraviolet light. And then infrared spectroscopy is here in the infrared region. So I love this figure because it shows you the UV VIS spectroscopy here. That's where we're operating. And it shows you the IR spectroscopy here. Now, NMR spectroscopy, which we're going to look at in our next chapter next week, operates here in the radio waves region. So that's where these fall. So these are really focused on this interaction of matter and light, right? Now, a few things to be aware of. The wavelength of these increase as we go this way, which means the energy increases in the opposite direction, right? So increasing energy goes this way and increasing frequency. So gamma rays have the highest energy. They're going to have the highest frequency. Over here, radio waves are going to have the lowest energy and the longest wavelengths here. So, one of the things, I love practical applications. One of the things that you've probably seen recently have been infrared thermometers. We use these in cooking a lot of times. They're super fun. And what they do is they focus the IR radiation emitting from something, right? If it's a thermometer that's taking your body temperature, onto a component called a thermophile that absorbs the energy. As the thermophile warms up, it produces a voltage, and that is converted to a temperature readout, which is just kind of interesting there. So we see a lot of kind of these practical applications. So I'm sure the burning question in your heart is, okay, Dr. Pierce, we're here. We've done a quick review. What's this new information we're going to learn? Well, we're going to start by learning about the IR spectrometer. So a lot of things are going here. These are going on here. These are labeled as 1, 2, 3, 4, 5, and 6 for you. So you can see the red numbers, and we'll talk about those. I always love to kind of start over here, just because this is what a lot of times students will see the very first time is a spectra like this. And that's the end result. Okay. And so when we talk about this, this is what you're going to see on this computer readout. That's what we're going to analyze. So in IR spectroscopy, what we're doing is we're examining the interaction of a sample with the radiation from the IR region of the electromagnetic spectrum. Now, remember, IR, infrared, is going to be wavelengths of anywhere from about 800 nanometers to 10 to the 6 nanometers. And it's completely invisible to our eyes, but generally we feel it as warmth. If you work in fast food and you have fast food lamps, infrared radiation is emitted from those lamps. It keeps food is warm. It's also responsible for the heat from a campfire or when sunlight shines on your face. So even though we can't see it, a lot of us have experienced it. Now, as I mentioned before, this is the general setup for modern spectrophotometer. Let's start over here with one. Okay, so what happens here is here's your IR laser, and a beam of infrared radiation is directed towards the beam splitter. So the beam splitter here is at 2, okay? And what that does is it transmits half the beam and reflects the other half. So if something is transmitted, it goes through, and if something is reflected, right, it's going to bounce away. So this is reflected at a 90-degree angle, right? So you can see here, it's the reflected beam goes here, and then this is the fixed mirror here. Now, that transmitted beam, as we mentioned, goes towards the fixed mirror, and then the reflected portion is guided back by a movable mirror. So that's a mirror that's movable within the instrument. Okay, and so they're guided back here. So if you follow kind of the arrows, it goes bzoop, 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 to where it gets like really, really dark here. And then this one goes zoop, and back, and to where it gets really dark here. The sound effects are completely optional there, but it does make it more fun. Now, when we've reflected these back, they're combined, okay? And they're recombined, and that recombined beam is going to travel through the sample and then is detected. Now, the sample here has to be transparent, and so a lot of times what we do is when we're preparing the sample, we use a press, and if it is a solid, it's pressed into KBR. And so you use a lot of force and it's pressed into a solid pellet with potassium bromide. It will turn out to be clear with the high pressure. The only problem is that KBR is very hygroscopic, so it will suck up water from the atmosphere and get cloudy pretty quickly. So you do have to do these pretty quickly. The other thing that you can do is they have some KBR salt plates. And so if your sample is a liquid, you can just inject a little bit of a liquid there. Now, when you do that, the liquid can't be in water because they're salt plates. So you have to use some sort of non-polar solvent. And so that's got to be the clear part that goes back through. Now, that beam hits the detector, and right, and so in it, the detector reports out our spectra, which is here. At the detector, what's going on is there's a measured intensity, and it increases and decreases very quickly over time because that moving mirror changes the way that the waves build up or cancel out, and that's constructive and destructive interference when those split beams are recombined. And so we can apply a mathematical algorithm to that fluctuating intensity, or that intensity that changes. And a computer will determine the intensity at each wavelength of radiation, which is the I detected here, and it compares it to the laser source, which is here, okay? So measuring these two, right, gives us our percent transmittance, which is times 100% here. Now, the intensity that's here, right, so that I stands for intensity, is a quantity that has units that are watts, but those units cancel. So generally they're not included when we talk about it at this level. Now, if you go on and take instrumental analysis, or are currently in instrumental analysis, I'm sure there's a lot more detail that goes in that's just really outside the scope of this course. So here's what I get really interested in and excited about is the information that we get from the IR spectrometer once we've run a sample. And so let's look and see, this is what the readout will look like. You see percent transmittance here, and then you see wave numbers here. I want to take a second to look at wave numbers. So wave numbers are measured in centimeters. So these are going to be centimeters to the -1. And that means it's 1 over the wavelength. Again, in centimeters. So it's what we call the inverse, okay? Now, for historical reasons, which really just means this is how it started and we never really stopped doing it, Wave numbers increase from right to left along the axis. This is different than almost all the other spectroscopy that we study. So just be aware of that. The bigger number is going to be here. The smaller number is going to be here. And generally what we see is a range of 400 to about 4,500 or 4,000 wave numbers. And that's what we see. You're also going to see here, these are our absorption bands, and those are the bands that we are most interested in when we talk about spectroscopy. Certain functional groups will give certain absorption bands. And so where these bands are located can tell us if a molecule has a certain functional group. So when we look at this, right, we have frequencies where the transmittance is here right at 100%, and that's really the baseline, right? So up here is really the baseline. And so what that means is most of the IR, so most of that infrared radiation makes it through to the sample to the detector. Right? And so every time you get a dip, though, what's happening here is that IR radiation is being absorbed by the sample. So less radiation is making it to the detector. And these dips are called absorption bands or peaks. Now, a strong absorption is one whose, as we mentioned, percent transmittance is near 0, which is going to be near the bottom of the spectra here. And so you also have a weak absorption, and these are going to be where peaks transmittance is near 100%, which is near the top of the spectra. Okay. Now, in the next screencast, we're going to learn how to use the IR spectra to determine certain aspects about the molecule structure. But we're going to talk some more about just some general theories behind IR spectroscopy first. For example, like, why do we get these stretches when light hits? Or why do we get these peaks when light hits? Well, one of the reasons is because the bonds move. They can stretch. So in chapter 1, we talked way back, we talked a lot about chemical bonds and how they can behave like springs. And so what I mean by that is those atoms of a molecule, it's almost like the bonds themselves are springs. And so these two guys can vibrate. And so during different types of oscillations, whether it be stretching or bending, there's two real types we're going to focus on. The distances and bond angles can vary, and they vary rhythmically, okay? And so they undergo different types of vibration. So the two big ones that we get are stretching and bending. So when we talk about this in stretching vibrations, what we see happening is the distance between two atoms in a chemical bond grow longer and shorter, okay? Now in bending, right, an angle, either the bond angle or a dihedral angle, becomes larger and smaller. Okay, so there are different types of stretching and bending, and when you come to class, I have a really great website that we're going to look at that shows those stretching and bendings. But if you look here, here's a carbonyl group. This is a carbonyl group of formaldehyde. And what you can see here is that there's some stretching between the oxygen and the carbon, okay? And then there's also stretching between the carbon and the hydrogen. Now, notice when we talk about this, you're going to see symmetric stretching and asymmetric stretching. In symmetric stretching, the bonds lengthen and shorten together, right? So these are lengthening and shortening together at the same time. In asymmetric stretching, like this side gets small, but this side gets long, right? So it doesn't happen at the same time. We can also see some bending. There are two types of bending that this book talks about. There's in-plane bending, where these two come down at the same time and these go out. And then there's out-of-plane bending, where the atoms periodically are going to occupy the same plane. And like I said, I've got some visuals for this, which are much better than the words and the arrows and those types of things. Now, for each of these vibrations, only a certain amount of energy is allowed. And when we talk about this, this kind of helps us look at that. So these are the energy levels way back from when we did energy diagrams, okay? And it's showing us the representative energy levels available for one type of vibration in a molecule. And so at room temperature, that vibration, right, which is represented here, is generally found in its lowest energy state, and that's called a ground state. Okay, so that's what we see there. Now, when IR comes in, that vibration, an IR photon comes in, it hits it, and that IR vibration can be excited to the next level. It comes up here and goes, whee, because it gets really excited, okay? And if the molecule absorbs a photon, right, whose energy matches the energy difference between these two levels, right, that's why it gets excited. Now, only IR photons of a certain energy can be absorbed by a molecule, okay? So that means that not every type of energy is going to excite a molecule. And so what we see here is the frequency where the photons are absorbed. The frequency where the photons are absorbed the transmittance decreases. And peaks appear in the spectrum. So the fact that, remember, IR has a wide range of energy, right? And so the fact that this particular stretching frequency only absorbs one type that will make this go to a higher energy level so that we can see it is the reason that we get peaks, right? And things that differentiate, because not all energy is going to make it do that. So very, very neat, very exciting. When we talk about this, right? So the frequency where the peak appears is typically the same as the frequency of that vibration that's responsible for the absorption of the photon. So I got real excited on the previous slide, and I probably was not as eloquent as I wanted to be, which is why I typed it out here. I knew I would. And so if we look at this figure here, what we can see is we've got peaks here at 2961 and a peak at 1717. And so the molecule that produces this IR spectra has types of vibrational motion with these same frequencies. And the beautiful thing about this is that functional groups will have the same vibrational frequencies or very similar vibrational frequencies to each other. So for example, alcohols will vibrate in a certain place, or ketones will vibrate in a certain place. And so we can relate these peaks to functional groups. So this this gives us another piece of unknown molecules. So we can use mass spectrometry to help us figure out, the molecular weight of an unknown. Well, this piece, IR spectroscopy, can help us figure out the functional groups that are in an unknown molecule. And so we're going to talk more about that in our next screencast.